All right, guys, welcome to 7.2. In this lesson, we're going to look at pedigree charts. All right, so a pedigree chart is a diagram showing the inheritance of a particular trait within a lineage. All right, so here's a pedigree chart right here, right? Now, they determine two things. Number one, they're going to tell you whether it is dominant or recessive in terms of the trait. It doesn't tell you whether it's incomplete or codominant. And then it also tells you whether it's autosomal, X-linked, or Y-linked, okay? Now, a couple of things that we need to understand about the trait, okay? So first of all, these numbers along the side tells you the generation that it's in. So there's generation 1, 2, and 3. And then these numbers tell you the individual number. So individual 1 from generation 1, individual 2 from generation 2, individual 1 from generation 3, okay? If it's square, it's a male. If it's a circular, it's a female. And then if they're shaded in, it means they have the particular trait that we are investigating, okay? And then if you have a mating line, it'll attach horizontally, and then the children are kind of little forked branches below. If it's twins, it'll have a forked triangular one, and then if it's identical, it will have a horizontal bar along the ones down here as well, okay? Now, there are 5 possible determinations that we're going to help in this particular chapter for you to figure out whether a condition is autosomal dominant or autosomal recessive or X-linked dominant or X-linked recessive or Y-linked, okay? And we're going to go through the patterns of each one of those traits to help you figure out the lineage, okay? So here's a bit of a test one. Without any knowledge whatsoever, I want you to try and figure out whether this is a dominant or recessive trait based on what you've known so far. So pause the video, give it a go, and then if you are ready to give up and die on the inside, you can go ahead and play the video. Okay, here we go. So this is a dominant trait. Why is it a dominant trait? Well, remember that in a dominant trait, all affected individuals, they are going to have at least one affected parent, right? So the giveaway for a dominant trait is that you can always trace the individual's lineage, and if an individual has the trait, so for example, 2, 4, and 5 in this generation have it, that means one of their parents had it, which is in this case the mom, right? The second thing to tell you that it's a dominant trait is that once it disappears from a branch, it will never reappear. So you can see here, this trait is not present in individual 6 in the second generation. They get together with another individual 7 from from somewhere else, and then you can see none of their kids are going to have it, right? So once it disappears, you're not going to see it reappear. Now, when you have a dominant trait, you need to identify which genotypes are going to give you that particular dominant trait, right? Remember, a dominant trait means that by having a capital letter, it's going to be affected. If you have a heterozygous genotype, you're still affected. But if you have 2 lowercase ones, you're not going to be affected, right? So we can actually identify the genotypes of these individuals based on this chart. How do I know that? Well, let's take a look at all the individuals that are not affected. And we're going to start by putting lowercase a in all of those individuals. So we assign lowercase a to unaffected individuals first, since there is only one option. If you don't have the trait, and it's a dominant trait, then all these individuals must therefore have lowercase a, right? Now, the second thing you're going to then do is if the individual is an affected parent, right? The parent has to be heterozygous, right? If they have both affected and unaffected kids, right? Why? Because there is no way this parent here could be 2 capital A's, because if she had 2 capital A's, all her kids would get at least 1 capital A, and they would all exhibit the condition. But because you can see 2 of the kids don't have it, that means she has to be heterozygous. So this mom has to be heterozygous here, right? Same here as well, right? So you can see there, this son doesn't have it, which means that this has to be heterozygous here. And then same here as well, where this individual doesn't have it, so this has to be heterozygous here. So you can go ahead and fill in the possible outcomes from the heterozygous individual here, and you get voila, right? Capital A, lowercase a, capital A, lowercase a here. And you can see here, as a result of that, these individuals all must have capital A, lowercase a. Now, you can also figure out this individual here and this individual here. Why? Because because mom and dad don't have two capital A's, there's no way any of the kids can have two capital A's, right? It's just not possible, right? If for that to have happened, dad would have had to have a capital A here and would not have the trait. Would have the trait. Okay, so that's how you can figure these things out, right? So we've pretty much actually in this case figured out everything, right? Now, anything outside of this, you wouldn't be able to differentiate, but luckily for us, we can, okay? Now, let's look at the characteristics of a recessive trait. Now, here is another lineage, and you can see this lineage is quite different from the other one. So previously, you can see there, this lineage exhibits individuals which, you know, travel down the branch in every branch, and then when it disappears, it actually disappears. Here, it can reappear. So mom and dad, they look normal, but they have a kid that has the condition, right? And so unaffected parents can still have affected parents, and that when you see that, that will tell you that it's a recessive trait. It's a recessive lineage with a recessive trait. If both parents will have it, all the kids will have it, and a trait can disappear and reappear and seemingly skip a generation, right? So if you identify the genotypes here, right, a lowercase a and lowercase a will be affected, whereas the heterozygous genotype is going to now be unaffected, right? So you can once again plot out your genotypes based on what we understand, right? So if you look at this and you go, hey, look, mom and dad don't have it, but the kid has it, must be recessive, okay? And then you can start plotting out your genotypes. Lowercase a means they're affected, so you go ahead, this guy, also this girl, these two guys here, these twins, this guy, this girl, this guy, this girl, this guy, this guy, they're all going to have it. So you plot out the affected individuals first, since you only have one option, and it's right there. Now, if parents are unaffected, but they have affected kids, the parents must be heterozygous, right? They have to have a lowercase a, right? Why? Because this is the only possible Punnett square you can get where you have unaffected parents with affected kids, right? And so because of that, parents must be this particular genotype. So you can go ahead and fill out, so this individual here, 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 and here, right? All must be heterozygous, okay? Now, that leaves these individuals here. Well, based on these results, right? Based on these results, the remaining individuals are actually unknown. Their unaffected kids can either be capital A or capital A or capital A lowercase a. Why? Because here are the only possible outcomes left, and we don't have enough information to deduce whether or not these individuals are one or the other, okay? You can probably do a test cross and figure it out later on, but you can't based on these results alone. So this is the genotype listing for that particular pedigree. So how do you know whether a condition is autosomal? Well, because it's autosomal, it is going to be on the first 22 chromosomes, which means that the number or proportions of males and females affected should be exactly the same, okay? Now, we count transmission from fathers to sons and daughters and transmission from mothers to sons and daughters, and not the external individuals, right? So here are the two previous pedigrees, and you can see here, right, I would count this individuals here, 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 and here. Now, you don't count this particular individual. Why? Because that's not a son, that's a mom, right? And so sons and daughters are here, here, and here, and all the following generations. So it's a 1, 1, 1, 1, 1, 1. So it is 3 here and 3 here. So that means that's equal. So that's going to be an autosomal trait, and not a sex-linked trait. Now, this one here, right, this count might look uneven. So if you count the number of individuals, you see 1, 2, 3, 4, 5, 6 boys to 1, 2, 3 girls. However, one of the things that we need to be aware of is, first of all, this individual here, right, they're twins, so they actually count as one, and then this individual is an external individual, so that you don't count the external individuals. Why? Because there's no traced lineage there. So the trait would only count 1, 2, 3, 1, 2, 3, 4, right? And so it is roughly even, roughly the same. So it's most likely going to be autosomal. Now, we can't say with absolute certainty, but for now, we can say with a bit of confidence that it is going to be autosomal and not sex-linked, okay? Okay, now let's take a look at X-linked traits. So characteristics of an X-linked recessive trait, that's going to actually show up different to characteristics of an X-linked dominant. So pay close attention to this. This is where it gets kind of a little bit more complicated, okay? Now, here's a pedigree showing an X-linked recessive trait. All the sons of an affected female are going to be affected, right? all the daughters of an affected male will be carriers. Sons cannot inherit the condition from their fathers. And in a large sample, more males than females are going to be affected. How do we understand this, right? So let's look at this individual here, this little line here. Both the boys have it because mom has it. Why? Mom gives the X chromosome to the sons, right? So if mom is, if she has the condition and it is a recessive condition, she must have two lower cases. So two lowercase a's, for example. And that means both the boys are going to get it 100% of the time. The daughters of an affected male, they're going to be carriers. Why? Because an affected male, so for example, this individual here has a lowercase x chromosome, right? Which means that all the daughters are going to inherit that lowercase x chromosome. However, because mom's in the all clear, there's a good chance that the daughters are not going to have the condition, right? Sons can't get it from the dad, so you can see there are no examples where the dad who is affected is going to result in a son. And then in a large sample, you should get more males. So you get 1, 2, 3, 4, 5, 6 males affected and 0 females affected, right? This doesn't quite count because she's an external. You don't count that particular proportion ratio, right? Now, notice how that the characteristics of a recessive trait still appear. So you can see how these two guys, they don't have it, but their kids have it. So that tells you it's a recessive condition. So even without seeing and understanding this particular trait, you should be able to figure out that it's recessive, right? Because these guys have it, but their parents don't have it, even though, mom's a carrier. Okay. Now we can also identify the genotypes, right? So let's map out your genotypes because it's going to look different between boys and girls, right? Capital A, or capital A, lowercase a gives you an unaffected female. Lowercase a gives you an affected female. Capital A, Y gives you an unaffected male. And lowercase a, Y gives you an affected male. So you can go ahead and fill in the ones. So we're going to start by actually assigning unaffected people first because that will tell us what their genotypes should be, right? So we can actually put in unaffected males and affected males because there's only 1 or 2 possibilities there, right? So you can go ahead and put that in there. You can assign lowercase a to affected females, and then unaffected mums must be heterozygous if they have any affected kids, right? Doesn't apply to dads. Why? Because if the mum is unaffected, but the kids have it, she's passing something on to the boys, right? And so therefore she has to be a carrier and she can't possibly be homozygous dominant. Otherwise, none of the boys would have it. Okay. Outside of this, the female genotypes can't actually be determined. So these two individuals here, we can't actually figure out what they are. Why? Because they could be either of those two, but we just don't know. Okay. All right. X-linked dominant traits. Now, you're going to get a different characteristic once again. All daughters of an affected male will be affected, and over a large sample, you're going to get more females than males affected. You see a reverse trend, right? So now, daughters of an affected male, they're going to inherit the X chromosome from the affected male, right? And they're going to get it, right? So here, so actually, I'll show you the genotypes just so I can show you here the mapping, right? So affected males, capital A. So that allele, that's going to go to all the girls. So 1, 2, and 3 are all going to get it. 1 and 2 will all have it. And remember, because it's a dominant trait, right? Affected kids will have affected parents, and then when it disappears off a trait, it's not going to reappear again as well, right? Now, over a large sample, right? 1, 2, 3, 4, 5 individuals are girls to 1 individual that is boys that are affected. So you can see that it's most likely going to be an X-linked condition, and it's X-linked dominant because more females are affected than males. Remember, when it comes to X-linked dominant condition, that heterozygous genotype, that's bad. It means you're going to be affected, and so you're now going to be more likely to be affected if you're a girl. Once again, we can assign all the simple ones first. So for example, we know each of these have only 1 possible outcome, so we can go ahead and fill them in. So affected males, they're going to have this chromosome, this genotype here. Unaffected females are going to have this genotype here, and then unaffected males are also going to have these genotypes. So you can go ahead and fill them in. Affected dads and unaffected mums will always give you a heterozygous female. So now we can actually figure out all of the genotypes, right? Yeah, so that kind of makes it a little bit easier for us to figure out, right? Now, the last one is what we call a Y-linked trait. Now, characteristics of a Y-linked trait is dead easy, right? You look at it, it is only going to be on the Y chromosome, which means only the boys have it, and therefore there is no dominant or recessive aspects at all, right? Because you only have one Y chromosome and it's either expressed or it's not present, right? So affected males will pass it on to all his sons. So you can see there, this individual here, his sons will have it, and then their sons will have it, and then their sons will have it, and likewise here and here, and none of the daughters will inherit any of those conditions whatsoever. However, if the daughter marries an unaffected male, then obviously it also exits there as well. Okay, so that's pretty much it really. All right, so that's it for this video. I'll see you guys in the next video for dihybrid crosses.